My name is Emily Halford, and I work in suicide prevention data analytics at the New York State Psychiatric Institute. In this video, I will be talking about how to use generalized estimating equations and multi-level modeling to use regression when your data are correlated. I'll start out by giving a quick conceptual overview, then quickly describe the sample data we'll be using, and then walk through two separate R code tutorials. Let's get started.
Linear and logistic regression are both incredibly easy to apply to almost any data in R, but that also means that they're incredibly easy to use incorrectly. In most cases, your code is going to run whether or not the regression technique you're using is really appropriate, so it's up to you to know if your analytic approach is valid. One of the most important ways to verify that your modeling technique makes sense is by checking the assumptions of that model type. Both linear and logistic regression have several key assumptions that have to be met in order for the results to be valid. For linear regression, these assumptions are as follows. 1, your observations are independent. In other words, knowing something about one observation doesn't tell you anything about your other observations. This one is bolded because correlated data is all about independence, so we'll be coming back to this assumption. 2, the relationship between x and y is linear, and you have to plot your data to check this one. 3 is homoscedasticity, constant variance of residuals at different values of x, meaning that as x gets larger or smaller, you're not getting a wider or narrower spread of your residuals. So the model fits as well at different values of x. And finally, normality, meaning that data are normally distributed around the regression line. So logistic regression has similar assumptions. First, you've got independence of observations again. Next is linearity again, but now it's linearity in the logit because logistic regression uses log odds rather than odds. And third, it's assumed that your model is correctly specified, which includes several conceptual things, including a lack of multicollinearity. Depending which resource you look at, you'll see different wording of regression assumptions and even some differences in which assumptions are included, but independence of observations will always be considered crucially important for both linear and logistic regression. Now, correlated data violates this independence assumption. Correlation can occur in two primary ways, and the first is shown here. We have individual observations, in this case students, but there's a second level to this data, in this case school, which groups students. Basically, knowing which school a student attends tells us something about what their individual observation looks like, so data points are not truly independent. These groups can be pretty much anything, such as neighborhoods, hospitals, or countries, like the example I'll be walking through later. In this example, individual observations are still the first level of data. Instead of students who can be grouped into schools, we now have data from various time points that can be grouped into individual subjects. So the individual observation at each time point is our first level, and the individual subject makes up the second level. It makes sense that multiple observations from the same individual are not going to be independent. In most cases, knowing which person a data point came from is going to give important information about that data point. So why does this matter? Most importantly, correlation prevents standard error from being computed accurately and often produces artificially low estimates. Fortunately, there are ways to use regression to get valid estimates when your data are correlated. The two modeling techniques that I'll be demonstrating are generalized estimating equations and multi-level modeling. GEE will give you estimates the same or similar to those produced with simple logistic regression, but with appropriate standard errors. It is ideal when the clustering isn't something you're interested in, you just want to get valid estimates. It also works best when you have many small clusters, which often occurs when you have multiple measurements over time. Multi-level modeling is best when you do actually care about the clustering and are interested in relationships both within and between clusters. MLM requires fairly large sample sizes within clusters, so works best when you have very large clusters. Okay, so I'm just going to quickly show you where you can find the data we'll be using in this video. So I'm going to use two different sources of correlated data for our examples. The first is data from years 9 and 15 of Princeton University's Fragile Families and Child Wellbeing Study. This is their website here. This study follows the families of selected children born between 1998 and 2000 in major US cities. Since the same families are followed year after year, data points from the same family units at different time points are not independent. Data are publicly available, although you have to submit a brief request on the data and documentation page, which is here. So the second data set is from the WHO's Global School-Based Student Health Survey, which aims to provide data on health behaviors and protective factors among students. Study data are available from many countries, but we will only be using data from Indonesia and Bangladesh, which can be accessed by going to Regions, and then Southeast Asia, and then clicking on the country that you're interested in. And you can actually go in data and documentation, and then we're using national data. This is where you can download the SAS file, and there also are these really useful code books that explain everything about the data. It is likely that children from each country are more similar to other children from the same country, so the assumption of independent observations is violated. Okay, so let's move on to the code. So I start out by loading the packages that we'll be using. So we have tidyverse for cleaning and manipulation, Haven because all of the data we're importing comes in SAS files, GPAC and GEE for running GEE models, and LME4 for multi-level modeling. So I'll be starting out with the fragile families data, which contains dozens of variables representing the health and well-being of participating children and their families. This data set falls into the bucket of that second type of clustering. There are data points from multiple time points that can be grouped into individual families. Since I work in psychiatric epidemiology, I'm going to build a model related to the mental well-being of participating children. The kids are asked if they often feel sad, and I'm using yes to these answers as my outcome. Substance use is known to be a predictor of poor mental well-being, so I'll use variables representing alcohol and tobacco use as my predictors. It's worth noting that this model and that which I'll use with the WHO data are not really meaningful. I haven't actually assessed confounding and mediators and other issues that might be present with the data. These are just for demonstrative purposes, and I just still like to work with data and questions that interest me regardless of the context. Anyway, let's start working with these data. So data from years 9 and 15 are in different files, so we have one code chunk to read in and clean each of them. The cleaning is separated because the variable names and coding differ slightly between study years. Otherwise, I would do that once after merging the files. If you're interested in these variables and coding, check out the data and documentation page I showed before with the code books. So I've selected the variables that I'm interested in because there are hundreds here, and then I assign meaningful, consistent variable names. You can see that's the same for year 9 and for year 15. And next, I filter to only include individuals with complete data for our variables of interest by excluding those with missing data or those who refuse to answer. So then variables are recoded in the standard 1 equals yes, 0 equals no format. For our outcome of feeling sad, this involved binarizing a variable with varying degrees of sadness. So 1 equals the child frequently feels sad, and 0 means the child does not frequently feel sad. Some regression techniques like MLM can handle multiple outcome levels, but I'm just binarizing here for simplicity. And then finally, this time order variable indicates if the data point is from the first or second year of the study. And this is important because data have to be sorted in a particular way later on for GEE to work. So let's just go ahead and run these. Okay, in year 15. Okay, so next we use rbind to stack together the data from years 9 and 15, which works well because all the column names are identical. So let's do that. Now we have one that has combined these two. And then finally, IDnum is converted to a numeric variable to facilitate that ordering. And then that ordering is done here in this final code chunk. So you can run that. And then that code gives us this final data frame, which you can see is ordered first by IDnum and then by this time order variable here, which gives the study wave. So let's move on to modeling. And we will start with a simple logistic regression model for comparative purposes. So we're using logistic because our outcome variable is binary, and we can specify this by adding the family equals binomial statement in the GLM function. And then tidy from the broom package just cleans up our output, which we can see looks like this. As you can see, tobacco and alcohol are both significant predictors of sadness among participating children. So next, we use generalized estimating equations by using the GLM function from the GPAC package. The syntax is really similar to what's used with the standard GLM function, but the ID, waves, and chorister, which is the correlation structure, arguments are new. So ID is used to specify the unique identifier that links observations with the same subject. In this case, it's our IDnum variable. then that time order variable that we used before or created before comes into play to specify the order that the observations were made in. And finally, there's this argument, which we have independence here, which is actually the default. So this is specifying our correlation structure, and often independence is what you want, but exchangeable can be used when observations within a subject can be considered equally correlated, and AR1 is best when the internal correlations change over time. In the text version of this article, there are some links with information on choosing the right correlation structure for your data. So we run that, and we can see that our beta estimates are exactly the same as those produced using GLM, but with standard errors that account for correlation to data. Our tobacco and alcohol use predictors are still significant, but p-values are somewhat different. Even though these changes haven't impacted statistical significance here, you can imagine that having correct standard errors could push a p-value over or under 0.05 if it wasn't as extreme as the p-values here. It's also worth noting that it might seem like the test statistic is wildly larger than that in the simple logistic regression model. That's only because here the output is a walled statistic and before it was a z-test statistic. So z-statistics are calculated by dividing the estimate by the standard error, and walled is that same value but squared. So they're mathematically related, but walled statistics are going to look much bigger. So with the GLM function, you'll also want to verify that your clusters were properly registered. And you can do this by just running the first part of the code here before broom tidy. And you'll scroll down to number of clusters and maximum cluster size. So we had 2 observations for thousands of individuals. So having maximum cluster size of 2 and then our number of individuals here makes sense. However, if you see the number of rows in your data set as the number of clusters and their size is 1, something is wrong. And your best bet is making sure that your data truly sorted correctly in your cleaning process. Okay, so now let's use GLMER from the LME4 package for multi-level modeling. Again, this code is almost identical to that used for simple logistic regression. The formula is the same, but with this bit in parentheses added. So random slopes are specified on the left side of the bar and random intercepts on the right. So our grouping variable comes in here as a random intercept, and if there were variables whose effects we wanted to vary between groups, they would come in on the left where the 1 currently is. So the LME4 package isn't compatible with Broom, so we just pull the model's coefficients after creating a summary up here. So first we run the model, and then we just pull out those coefficients. Okay, so again, we get similar output to the basic regression model. However, now estimates vary slightly because correlation isn't being ignored or treated as an annoyance. Now it's being treated as an important part of the model. Standard error estimates are higher here for all values than those produced with simple logistic regression. And our z and p-values are similar, but now reflect those important changes in the estimate and standard error. So which model makes the most sense here? I would use GEE due to the maximum cluster size of only 2 observations, the nature of the data with multiple observations over time, and the fact that it makes more sense here to try to account for clustering than to really try to dive into differences between these groups. Okay, so now let's try this with the global school-based student health survey data, which represents the other common kind of clustering. In this instance, you've got cross-sectional data from individual students that can be grouped into countries. Again, I'm going to stick in the psychiatric epidemiology vein for my model. In this case, I'll use variables describing whether or not a child has friends, whether or not a child is bullied as my predictors, and whether or not the child has seriously contemplated suicide as my outcome. Okay, so let's load and clean our data. Our files are SAS files again, so we use read SAS from the Haven package again. And then we follow a similar pipeline to what we did with the Fragile Families and Child Wellbeing Study data. Important variables are selected and given meaningful, consistent names. And then this country variable is created to indicate whether the student comes from Indonesia or Bangladesh, which are our 2 clusters. So we'll go ahead and run these. And then again, we use rbind to stack the data frames together. So unlike the Fragile Families data, variable names and codes were consistent between groups here, so we can do some cleaning on the combined data set. So here we convert all variables from string to numeric, and then binarize them in a consistent format and drop missing values. So now our final data looks like this. It's just very simple. Everything's binarized. Okay, so now on to modeling. Again, we just use the standard GLM function to run a logistic regression model using bullied and friends to predict suicidal thoughts. So we do that. And then unsurprisingly, we see that children with friends are less likely to have suicidal thoughts, and those who are bullied are more likely to have suicidal thoughts. So now on to GEE. And this function is less computationally efficient than GPAC, so I'm just going to go ahead and start running that. But so you'll see that we're using this different function now, and in my opinion, the GEE package is easier to use with data that is clustered by a grouping variable, such as country, rather than within an individual with multiple observations. So again, we've got our formula, data, now the ID argument gets country because that's what's grouping our data, family equals binomial to indicate logistic regression, and that correlation structure argument. So the GEE function also isn't compatible with tidy from Broom. So we again just create an object where we can take a summary of it when this is done running. So now a summary takes a minute to run. And then, okay, so one reason I particularly like the GEE function is that the naive standard error and z test statistic are included in the output. Naive just means that they were calculated without considering correlation, so the same as standard logistic regression. And you'll see that these values are actually exactly the same as those produced above with our basic regression. In our robust estimates, or those accounting for clustering, you'll notice drastic changes in the standard errors in z-test statistics, although the direction and significance of our relationships remain the same. It looks as though accounting for this within country correlation has allowed for much lower standard errors to be used. Okay, so now on to multi-level modeling again. And as I noted before, these models are for demonstration purposes only and aren't necessarily valid. For multi-level modeling, we would actually want several more groups than just two here, as in having data from more than 2 countries. If you really were just using 2 countries, you would want to consider corrections for small sample size, and there's a link describing this in the text version of the article. So anyway, the code is exactly the same as that used with the Fragile Family Study data, but now with a new formula, a new grouping variable, and our data set specified. So run, and then, oh yep, I'm gonna have to do that. And then again, beta estimates and standard errors have been adjusted to account for clustering. The z-values and p-values associated with bullying and friendship predictors are somewhat similar, although again, these both remain significant predictors. Okay, so what model is best to use for the global school-based student health survey data? In this case, I would use multi-level modeling, although again, we will want more levels. But this is because the data are cross-sectional and can be divided into large clusters by country. Again, it seems like we would probably be interested in diving deeper into the output to look at differences both within and between groups, meaning that clustering by country is something that's actually interesting from a research perspective and not just something to account for. In conclusion, regression truly is flexible, and there are techniques like GEE and MLM that let you use it with correlated data. It's just important to always check all assumptions of the models that you're using to ensure that your analysis plan makes sense and that your results are valid. Thanks so much for watching.